So hi everybody, my name is Ali Shirsavar. It's really good to be here. Over the next 50 minutes, I believe, I'm going to talk to you about a step-by-step snubber and clamp design for power supplies. We also have two spreadsheets that you can use in order to do all the calculations for you. So everything that we discuss here and all the equations that I give you, we can also use the spreadsheet, which will do basically the donkey work for you. So let's start with RC snubber and RC clamp design. Can I minimize this so that, okay, that's it. Okay, so many topologies require either a snubber or a clamp circuit to suppress the ringing and the spikes. The picture that you see is a typical one with that. This one is running without any snubbing and without any clamping. The spikes are usually generated because of some leakage inductance ringing with some capacitance, or some inductance ringing with some capacitance. As you can see right here, this is on a flyback converter. The high frequency ringing that you see here is the leakage inductance of the transformer ringing with the resonating with the parasitic capacitances of the MOSFET and the PCB. The one that you see here is actually because the power converter is in discontinuous conduction mode, and now that is the larger inductance of the coupled inductor or transformer, flyback transformer, if you will, ringing with some capacitors. In continuous conduction mode, this actually disappears. Flyback converters are notorious for having both a ringing and a large leakage spike. This is a spike over here. And of course, without the snubbers or clamps, these spikes and rings would put excessive stress on the device and blow it up. In this particular case, I've got a power supply that is supposed to operate at 12 volts in, 7.5 volts out. And I am still in discontinuous conduction mode. I'm somewhere around 10% load, and you can see that the spike here has already got to around 35 volts. If I increase the load anymore, it would actually blow up my MOSFET. Okay, so this is a 12 volt input flyback, and I've got 35 volts in discontinuous conduction mode. At full load, this spike would certainly kill off the MOSFET. And the transformer that I'm using on this flyback, it's a one-to-one transformer. And of course, the voltage on the secondary gets reflected back onto the primary. So if you had a 10-to-1, then this voltage here would be a lot higher. And of course, then this whole thing would shift even higher. Now, ignoring the snubber cap and the inductor resistance, just for the sake of analysis, we have a transfer function that looks like this. It's your standard LC second order underdamped transfer function. We've said that the L is usually due to the leakage, and C is various parasitic capacitances that we have. And comparing this directly with a standard second order system equation, whereby we have got something like this. You have got omega n, which is your resonant frequency undamped, and then you've got your Q, which tells you the amount of peaking, and i.e. how much a spike you're going to have. So if you compare that like for like, this is the S squared term, and this is the S term, and of course the 1 term, we end up with the undamped natural frequency of the whole thing being 1 over root LC in radians, or the one that we are more familiar with, 1 over 2 pi square root of LC, and Q would be equal to R the square root of C over L. Okay, now as you can see, Q is related to damping. This is damping ratio. Control theoreticians use damping ratio, whilst in power world, in filter world, we usually use Q. And Q is directly inversely related to the damping, and we would like to set the Q to 1 so as to damp the system in order to reduce the spike. Now, if I want to set the Q to 1, then R will have to be the square root of L over C. And you can see that the square root of L over C times the square root of C over L will give me a Q of 1. The equations are exactly the same for a second stage LC filter, which we have discussed in various videos before. So on the primary side of a flyback, we have the primary snubber. Here you can see the picture from the previous slide that I showed you. I've just enlarged it and expanded it, and I have measured the ringing frequency. So as we just showed in the previous slide, 1 over 2 pi square root of LC is the ringing frequency, and of course I can measure that on an oscilloscope. I have measured it with my scope, and I have got 25 megahertz. So all we need to do is calculate the parasitic capacitances in our circuit, and then we can easily work out everything else. Please note that even though the manufacturers specify the parasitic capacitances of your MOSFET, this is usually specified at a certain voltage, and the capacitance of the MOSFET is not linear or fixed. As the drain source voltage of the MOSFET increases, so does the capacitance. I believe is proportional to the square of the voltage. So looking the capacitance up in the datasheet is not going to help you very much, and that is why we determine it via measurement. So we measure the ringing frequency. It is we can measure L using our Bode 100. We have done many videos in which we have measured the leakage of the flyback transformer, and based on that you can calculate what is the real parasitic capacitance in your circuit. Okay. Then from the previous slide, let's say that we have measured the leakage to be around 250 nanohenries, and we know that the ringing frequency is 25 megahertz, then C would work out to be around 162 picofarads. Okay. Now, for a Q of 1, R is equal to the square root of LC, and R would be 39 ohms. And that is how we calculated the components that we need, right? So an easier way of doing this is to substitute the equation for the resonance frequency from the previous slide in order to just get one simple equation for R. So you can say that R is equal to 2 pi FRL, okay? Now, I've effectively just eliminated the measurement of the calculation of the capacitance. 2 pi, you know, resonant frequency, you know, because we measured it. L, the leakage, you know, because we know how to measure the leakage inductance of a transformer, and you plug these into the equation and you get 39 ohms. And of course, these are already in the spreadsheets that we have provided for you free, that you can download, and it will calculate the value of the snubbing resistor for you. Now, up until now, we've ignored the impact of the capacitor in our snubber. Its inclusion would make the equation actually very, very complex in order to calculate the transfer function. Instead of doing that, we are going to do a simpler version, which is the empirical method. The snubber capacitor, right, has got the following impact. The larger the capacitor, the larger the power loss, but better the Q. So if you solder a massive capacitor in your RC, a snubber, then your spike will be flattened out completely. But this capacitor stores energy and dissipates energy twice per cycle, once going in, once coming out, right? And although you may completely damp the spike, you end up dissipating quite a lot of heat into the snubbing resistor. So if we use a large capacitor, we'll get a very perfect correlation with what I showed you, and you get a Q of 1. And if you use a very small capacitor, you have lower losses, right? But a larger Q and more oscillation. Now, a good compromise, it very much depends on the circuit that you're designing, is to calculate the capacitor value such that the losses are limited to around 25 to 60 milliwatts, depending on the package size of the resistor that you are using. The reason I say this is that if you have got a small surface mount package and you're dissipating a lot of heat in it, you're going to get a hot spot and the PCB will blacken, and after a while it'll crack, and so on. So depending on the size of the resistor that you have got, you need to limit how much you're going to dissipate how much you can dissipate, and therefore size the capacitor. Even if you manage to buy a quarter watt or half a watt resistor, you still have to take into account how hot the PCB is going to get without causing damage. Another thing to note is that, let me go back a few slides. Okay, from this circuit, as far as the circuit is concerned, this part here, right, is the ground. So you can see that if you poured the copper down here, then the heat can dissipate from the resistor into the copper plane, into your ground plane, in order to dissipate the heat so that you don't get a hot spot. Okay, so the equation for the power loss from the snubbing circuit is C snub V snub squared times the switching frequency. For those of you with a keen eye, if you remember, the energy stored in a capacitor was half CV squared. So the energy, if you remember, was 1/2 CV squared. And of course, this is happening twice per cycle. So 1/2 times 2 gives you CV squared. And then that is the energy stored or work done in joules. And that multiplied by 1/time, which is your frequency, is going to give you the power. So that is where that equation is coming from. Okay, so let us have a look at how the shape of the ringing and the spike changes depending on the size of the capacitor that I use in my snub. If I use no capacitance at all and just let it ring away, so it will find some capacitance somewhere, there will be long ringing, and this is what you see in that oscilloscope plot that I showed you earlier on. It is dissipating somehow with some parasitic resistances and so on, and you get this green trace over here. Lots of ringing, lots of spike. This is normalized to 1 volt, so you've got around 70% increase on top of the 1 volt, right? So then, for the case that I am designing, if I sold at a 330 picofarad capacitor, then the losses will be equal to 25 milliwatts, but the Q is bigger than 1. That is this blue trace here, right? A Q of 1 is when you get a slight bump, but not too big a bump. So you are about 30% overshoot on the normalized 1 volt that you've got here, and I'm already dissipating 25 millivolts, right? If I use a 780 picofarad, the losses go up to 60 milliwatts, but you can see that the spike has been reduced to quite a low value. And that is almost a perfect match with the theory. And if we can tolerate 60 milliwatts of loss, then 780 picofarads would be a good value to use. If you use any higher value, then it probably will not give you much more. So you get to a point of diminishing returns here, whereby you're damping it far too much, but the capacitor every cycle, twice per cycle, will charge up and then discharge into the resistor. And of course, that will mean that your losses will increase. So a good compromise to calculate a capacitor is such that the losses are between 25 to 60 milliwatts to avoid hot spots on the PCB. And of course, that is related to the size of the surface mount component that you can use, your size limitations, whether you can go on a larger package or whether you're going to have a tiny package and so on. Okay, note that this snubbing voltage is the voltage on the drain at turn-off. Now, the equation for that in a flyback converter is V in plus N times V out, right? So V in is the input voltage, N is the transformer turns ratio, and V out is the output voltage. In the case of the one that I am presenting, the transformer turns ratio is in fact 1:1, and V out is 7.5 volts. So 12 volts plus 7.5 volts will give you 19.5 volts. But consider an offline flyback whereby you have got 230 volts on your input, and then you have got, let's say, a 10:1 turns ratio and a 10 volt output. So you've got 230 volts on your input, 10 volt output times a 10-to-1 turns ratio. That's 100 volts plus 230. That's 330 volts. So you can immediately see how this power loss, and that's squared then, right? You can see how this power loss can really shoot up. So in our case, it's low voltage. It's not too painful. The switching frequency is low. In particular, this voltage is small, and therefore we got away with soldering a 330 picofarad capacitor. Okay? That was the primary snubber. Now, on the flyback, you've also got the secondary switch or secondary diode. The procedure for designing that is also, it's very similar. Again, the first thing that you have to do is work out the resonant frequency of the ringing. You have to measure that with a differential probe because the diode is not with respect to ground. So at the diode turn-off, the secondary diode's parasitic capacitance will ring with the leakage of the flyback transformer. You can see that on this plot without any snubbing. The procedure for the design is exactly the same. So step one, you measure the leakage as seen on the primary with reference to secondary. We have done this in various videos with Omicron, and we have used the Bode 100 in order to measure our transformer. And our measured total leakage on the secondary side, in our case, is 215 nanohenries, mainly because it's a 1-to-1 transformer ratio. If you had a 10-to-1 transformer ratio, obviously that would have to get reflected back with the square of the turns ratio. Again, we have done a video that explains exactly how that is done. But for simplicity, let's say that we know the leakage, which is 250 nanohenries. We measure the resonant frequency from the ringing on the scope plots, and I can see from the measurement that this is around 17.5 megahertz. And then we, as I explained, this is the equation. In order to get a Q of 1, the snubbing resistance value from the equation that we derived earlier on is 2 pi times 17.5 megahertz times 250 nanohenries, and that gives me 27 ohms. And I actually soldered a 33 ohm resistor on the board, mainly because I didn't have a 27 ohm resistor in my box. There was no other scientific reason for using 33 instead of 27. Okay, let's look at the secondary snubber again. So the calculation for the capacitor value and the power loss again stays exactly the same. You have got power loss, you've got the size of the capacitor, you have got the square of the voltage, and you have got the frequency. That's the switching frequency and not the ringing frequency. The snubbing capacitor again determines how damped this peak is going to be, and at the same time, the size of it, as you can see from this equation, is going to determine what the power loss is going to be. Okay. So this is the ringing on the diode before the RC snubber. This one is when I have added the RC snubber. Again, the voltage is this time it's on the secondary side, right? So you've got 12 volts input divided by the transformer turns ratio, divided by the transformer's ratio plus the output voltage, which in my case is 7.5 volts. That is 19.5, right? So C snub, I've worked out if I wanted to have a 35 milliwatts worth of losses, 19.5 volts squared times 200 kilohertz gives me around 460 picofarads. I actually used a 470 picofarad, and that is giving me a 34 volt peak. You can see from here. So this is 19 and that is 34. Now, if your diode breakdown voltage is rated so that it can tolerate that, then that is fantastic. You're done. If your diode voltage cannot tolerate that because it's going to break by that point, then you're going to have to increase the size of the capacitor. And of course, if you increase the size of the capacitor, then your power losses will increase. And again, you would like to make sure that you can dissipate this. So that was the RC snubber. And I said earlier on that we have got a spreadsheet that allows you to do all of these calculations. I'll show you how this is done a little bit later. Now, on some occasions, in particular with flybacks, the leakage spike is so high that the RC snubber is just not enough. You saw earlier on, just from the previous slide, that here I'm already dissipating 35 milliwatts, and that's just a 12 volts in 7.5 volt out power supply. Again, with the case of the primary snubber, you can see that just in discontinuous mode alone, I am peaking so much. And if I go to the power loss equation, here, the input voltage for us is at the moment only 12 volts. Now consider 230 plus the output voltage reflect back to primary. It comes a point whereby the size of the capacitor becomes so big that the losses are simply not tolerable. And at that point, we move on from our RC snubber into an RCD clamp. Please note that we also have a circuit called RCD snubber. For those of you who have been in motor control and other power electronics fields sides of power electronics, there is a difference between RCD clamp and RCD snubber. The circuit looks identical, but the component values are actually different. So what we're talking here is an RCD clamp, whereby at a certain point, the diode will become forward biased and it will clamp or crop the top of the ringing, and therefore stops the MOSFET from blowing up. So on some occasions, particularly in flyback, where the leakage spike is very high and RC snubber is not enough, right? We would like to physically clamp or clip the peak of the spike in order to avoid the voltage so that we don't damage the FET. The most common is the RCD clamp. The circuit of it is shown here. It says expand panel to show video. I don't know what that means, but you can see it. You can see it over here. Okay. And I've got a leakage spike with RCD clamp here, and I have designed it so that it is clamping at exactly 30 volts. If you remember the previous plots, this in discontinuous conduction mode, this was going up to 35 already, right? This is in continuous conduction mode. You can tell it's in continuous conduction mode because there is no low frequency ringing here, right? So my power delivery right now is a lot higher, but the RCD clamp is kicking in, and I've designed it to clamp at 30 volts. And of course, the trick is, pardon me, obviously, how do you calculate the value of this R and this value of C so that the D gets forward biased at the voltage that you want, which in my case is 30. Okay, so for that, I have expanded my plot and I have defined a few things. V max is the bit that I want to specify. I don't want it to go beyond a certain voltage. Okay, so in the case of the flyback that I am using, I've got V in, which is my input voltage, and it's 12 volts. Your case would be different, maybe different. Then clamp, V clamp is to be calculated. So I want to calculate how much voltage on top of the 12 volts I can have so that I don't violate my maximum voltage over here. Okay, again, down here, if you have a look, I have got my V in plus V out reflected. So V in is 12 volts plus the output voltage reflected into the input. In my case is 17.5. Of course, it may be very different. You can also see here from my trace that I have got 29.8 around the point whereby I turn on the clamp. So if the maximum desired voltage on the FET is 30, so you don't want to go beyond 30, and your input voltage is 12 volts, then V clamp, I need this in my next equation, and this is what you need in the spreadsheet, then V clamp is 18 volts. So 30 minus 12 is giving me 18. So on the next step, so step by step then, first thing you do is you select the maximum voltage, Vmax, that you're going to allow on your FET at off time. The higher this voltage, the lower the losses in the snubber, i.e. if you allow it to have a bigger spike, then obviously you're going to have less losses in the snubber and the clamp circuit. Right, so we would like to find that sweet spot, the maximum amount of spiking that we're going to allow without damaging the FET. You could design one that completely crops the ringing just at the perfect voltage for you. But if you make that very low, then obviously your losses will increase. Now, typically a good number is 66% of the FET's maximum allowable voltage. Another way I've seen people calculate is 85% of the FET's maximum allowable voltage plus another 20 volts worth of fudge factor, you know, minus 20 worth of tolerance to allow for overshoot. So these are the things that I've seen in various application notes people use. And then as an alternative, you can calculate exactly how much power loss you're willing to tolerate in the clamp and then reverse engineer it and work out what is the maximum voltage that you can get away with a clamp. Christoph Basso's excellent book has got the entire subchapter, I think, on how you do these. And what we have taken here is the equations that he has derived in his book. So the reference is down here where these equations actually come from. So the step one is you intelligently work out what is the maximum clamp voltage you can get away with. Step two, you calculate V clamp. And of course, V clamp is the maximum voltage that you're going to allow minus your V in as per previous slide that I gave. Okay, then the step three, you calculate R clamp, right? And R clamp is worked out with this equation. So we got 2 V clamp, open bracket, V clamp minus NV out, right? V clamp we worked out here, right? N is the turns ratio of our transformer. We know that. Output voltage, we know. Fs is the switching frequency, we know. Leakage inductance of the flyback transformer, we know because we have measured it. And there are, as I said, there are videos that we have put on Omicron's website. We show how you measure that. And of course, the peak current, you also know because you have designed it. Okay, so that's from this too. As some of you may be aware, we have got a power supply design software called Biricha WDS, which is also available on our website. If you have designed your power supply using this software, it actually gives you the peak current. But in any case, if you are designing any power supply, you're going to have to know the peak current because that's the bit that blows things up. So we know all of the variables inside, and therefore we can calculate the value of the clamping resistor. Okay. Then, step 4, we calculate C clamp, the capacitance of the RCD clamp. Unlike the RC snubber, the value of the RCD capacitor does not impact the losses. So we are not too concerned about sizing it in such a way that we reduce the losses. It's therefore, its size is not crucial. You just needs to be large enough to keep the voltage constant during the snubber operation. It is essentially an RC circuit, so a good compromise would be 2.5 to 5 time constants, and that is the equation that you use. Again, you can have a look at Christoph Basso's book for how this equation has been derived. Okay, and then finally we calculate the total power loss of the snubber, and here you've got half the leakage inductance, I peak squared. Again, you can see half Li squared is the energy stored in an inductor. Fs is 1 over time. So that is giving you power. And then you've got this voltage here, V clamp divided by V clamp minus NV out. V clamp, you know, turns ratio, you know, and V out, you know, and that is giving you the total power loss. Okay. If power loss is too much, then you need to increase the clamping voltage, which could mean buying a bigger FET. So, in our workshop, we design these and we demonstrate how it's all done. Step 1 and 2, the workshop flyback that we use is 12 volts in, 7.5 volts out. The transformer turns ratio 1:1. So V in and NV out, we know. 2.5 amps again is from WDS. This is from the workshop a flyback. Actually, I am running a workshop right now, so I can show it to you. Just bear with me 1 sec. So there you go. That's a tiny flyback that we use in the workshop. That's your transformer, and the point around here, I don't know if you can see or not, is the RCD clamp that we designed. So we select a maximum voltage of 30 volts. So I don't want a voltage higher than 30 volts on my FET, and that will give me a V clamp of 30 minus 12, which is equal to 18. Then I stick it in this equation. There is nothing there that I don't know. 2, I know. V clamp, I know. Turns ratio, I know. V out, I know. Switching frequency, I know. The leakage, I know. And the current, I know. And that gives me an arc clamp of 1.2 kilo ohms. Okay, this is the value that you need to ensure that the diode switches on at exactly the right voltage. And note that the one for the RC snubber was in orders of 20s and 30 ohms, while this one is in order of kilo ohms. Then cap value is not really crucial. You get to 2.5 to 5 time constants. Our clamp we've just calculated. Switching frequency we know, so anything between 10 to 20 nanofarads, and in fact the one that I soldered on this board is around 10 nanofarads, and that is giving me quite a nice clamp. Okay, then let us calculate the total power loss. The total power loss is half of the leakage times I peak squared times switching frequency times this. Again, as I've mentioned before, we know all of this. Right now, 267 milliwatts is a little bit too big for my liking. Right, if I were to design this, I would change my parameters so that I would I would have less losses. However, as I don't know whether you can see or not, but the resistor I have soldered to this massive plane down here, so the heat that is being dissipated in it is nicely dissipating into a copper plane, and I have measured it, and it's not too much, and I've also used the 1210 package in order to make it tolerate more heat. This is the results. So this is my measurement. Note that the clamp only clamps the voltage, does not take away the ringing, right? The ringing is job of the snubber. Now, this is the RCD clamp only, right? And we designed it to kick off at 30 volts, and it does. It's around 30 that it actually, the clamp comes into action, and it clamps it, and it protects the MOSFET. What I could also do if I wanted to reduce the ringing is to add an RCD clamp plus an RC, a snubber. And that is the case that you see over here. Now, whether or not that is necessary or not depends very much on whether this 25 megahertz ringing is going to show up in your EMC test or not, right? So when you have protected your FET, then you have protected the FET. So the job of the RCD clamp is finished, right? But then at some point, the product is going to have to go to the EMC testing house. And if this thing here, oops, I beg your pardon, if this thing here is ringing at 25 megahertz, then that is going to show itself. So you may wish to add the RC snubber as well. What I normally do if I have a space is I put the footprints on, but I don't populate them. And then when we go to the testing house, or when we can actually measure the conducted emissions in the lab here. So when we measure the conducted emissions, if I see spikes around the ringing frequency of various snubbers, various switches, then I add the snubbing as well in order to try and get rid of that. Okay, so I'm now going to quickly show you the website for downloading the spreadsheets that will do this. You go to our website, you go to more, right, and you've got the snubber design and you've got RCD design. So if I click on that, there you go. On the more, you can download both an RCD clamp and a snubber, and also on both of them you get the transformer parameter referral. So on this one, you can refer parameters from primary to secondary and secondary to primary. Now all the red cells are the results, and all the yellow cells are the ones that you have to type your stuff in. So step one, right, ringing frequency of the on the FET, there's resonant frequency. For simplicity, let's say it's 30 megahertz, okay? And then the total leakage of the transformer, we use the Bode 100 in order to measure it. Let's say it is, who knows, let's just keep it as it is, 250 nanomes, right? Then the input voltage across the V snubber. Now you can work this out from the equations that I've given you in the presentation. Now, if you don't know how to, or you're uncomfortable with how to refer voltages from primary to secondary of the transformer or secondary to primary transformer, you just go to this transformer parameter referral tab, and here you can just type in your values and your turns ratio and your voltages, and it will work it out for you. Now, for simplicity, let us say that we have got 20 volts. That is, oh, wrong place. 20 volts, right? And then in step 4, right? Maximum allowable power loss, right? Let us say that I'm going to allow 50 milliwatts. 50 milliwatts. Switching frequency of my power converter, let's change that from 200 to 400, right? And everything else should be calculated for you. Okay, so it has worked out a snubbing resistor of 47 and a capacitor value of 312 picofarads. Obviously, we cannot get these exact values. 47 is close enough, so I'm going to use 47 here, right? And let's say, as soon as I do this, you should see that the power loss will stay the same. But as soon as I change the capacitance, you'll see that it's going to change. So the spreadsheet is calculating the capacitor to be 312 picofarads, right? So if I do 330 picofarads, the power loss is 50, right? And that is what I wanted. So it is not too bad. Now, this may or may not give me the right amount of the snubbing. So it may or may not be the case that the peak is not low enough. And let's say that I have to solder a larger value, right, in order to reduce the amount of the size of the spike. But just see what happens to the power loss when I do this. It goes to 75 milliwatts, right? If I want to lower it even more, let's say 680 picos, and now it's 100 milliwatts. Now 100 milliwatts is quite a lot, and at that point you turn around and say, you know what, I don't want to use this, I'm going to need a clamp, or I'm going to need both of them. So now I get a second opportunity not to cock it up and show you how you go and download it. So I'm going to stop sharing, right? And then I'm going to go and share, okay, our website. Okay, here. Can you see the website, guys?
Yes. Yeah.
Okay, so you go to more, and here you've got transform measurement, a snubber design, RCD design. A snubber design I've just done. So you go there, you click that, right? It will ask you for your email address. If you already got an account, that's all you need to do. And then when you click on that, an email will be sent to you with just the link. There you go, and you just download it, right? And that will download the Excel spreadsheet for you. You can see the RCD clamp here. Yeah. Okay. So, and then I'm going to open that. So I need to stop sharing. And when that opens, RCD clamp, editing, and share and RCD clamp. So this is the second spreadsheet, which is available for you. Again, you will be familiar with the waveforms that I showed you on the presentation. Everything is defined exactly the same as the presentation. This is the circuit. This is your RCD clamp. Again, the yellow cells is the ones that you need to fill in, and the red cells is what is going to calculate for you, right? And again, you've got the transformer parameter referral tab or sheet if you need to refer any parameters from primary to secondary or vice versa. Now, again, step one, input the maximum allowable voltage on your device, right? Let's say you have got a 600 volt MOSFET and you're going to allow 500 volts on it before you start clamping. You may get silly numbers this time, but have a play, right? Okay, that is you're going to allow 500 volts, right? And let's say that the input voltage is 48 volts. Okay, let's say that your flyback transformer has got a turns ratio of 10 to 1. Okay, let's say your switching frequency is 200, right? Let's say that your output voltage is 12. Let's say the total leakage is as seen is saying 250, and here, right, everything has been calculated for you, right? So this is the size of the RCD, the resistance. This is the size of the capacitance, and this is the total power loss. And as you can see now, the power loss is 200, right? And 200 milliwatts is quite a lot. If I allow this voltage to go higher, I expect that to go down, which it does. Yeah, but you need to find a compromise, and it's an iterative process. Okay, right. I think that is the end of my presentation. Thank you very much for your time. Stop sharing, and I am now available to answer some questions.